Ja, god middag alle sammen, og velkommen til Realfagsbiblioteket her i dag og dagens GeoOnsdag. Mitt navn er Bernt Edselmüller, og jeg er da for tiden instituttleder ved Institutt for geofag her ved Universitetet i Oslo. Og i dag er vi jo fullt hus, og vi er så lykkelige at denne dumme koronaen den er jo ikke over, men vi får i hvert fall lov å møtes. Det er veldig bra. I dag har jeg den store gleden til å ønske velkommen professor Kirstin Krüger, som er ansatt her ved Universitetet i Oslo ved Institutt for geofag. Så Kirstin er professor i meteorologi ved instituttet, og hun har studert meteorologi i Berlin og har en PhD der fra 2002. Og deretter har hun arbeidet både ved Alfred Wegener Institut, AWI i Potsdam, og senere ved Christian Albrechts Universitet i Kiel. Er det korrekt? Geomar sammen, ja. Så hun kom til Universitetet i Oslo i 2013, ja, nesten 10 år siden. I 2018 fikk hun tilslag til et toppforsk- eller fellesløftprosjekt med navn VIKINGS, der hun bruker kompetansen hennes om hvordan partikler flytter seg mellom atmosfæren og stratosfæren til å forstå bedre hvordan vulkanske erupsjoner har påvirket klimaforhold under tidligere tider, blant annet vikingtiden. Så, og dette her er nå grunnlaget for hennes presentasjon i dag, som heter Vikings, Volcanic Eruptions and the Impacts of Climate, Environment and Viking Society in 500 to 1215 Common Area. Så, da ønsker jeg Kirstin velkommen til å holde dette foredrag, og hun skal talk English. So, please, the floor is yours.
Thanks a lot, Bernd, and thanks for the audience. And it's a great pleasure for me to present our results from more than 3 years of the Vikings project, which got funded by the Research Council of Norway and also by the University of Oslo. And this is a big team effort. And a lot of my team is sitting here. In case I can't answer some of the questions, they will help me out. Okay, and I will tell you more about what this picture has to do here in that context. So, what do we know about volcanic eruptions and their impact on climate? And here I show time series of the past 2,000 years. On the top, you see big, large, explosive volcanic eruptions. And below, you see the temperature effect over northern hemisphere land. And big, large, explosive eruptions, which include a lot of sulfur injecting in the second layer of the atmosphere, they lead to a cooling of the surface. I will explain that a little bit more. So you see here, large eruptions are highlighted. For example, the unknown 536-540 double event, or Elgja in Iceland, 939-940, and some others. You can also hopefully read out that these cold periods, so we get up to decadal or multi-decadal cooling following these large eruptions, that they also seem to have some impact on society at that time. The Great Migration following the unknown eruption or the Little Ice Age, for example, are connected with that. So the large climate variability of the past 2,000 years is mainly due to the volcanic eruptions. So, but the question we are investigating here in this project is really a key. So there were also the Vikings from 800 to 1050. They must have also been impacted. There were a lot of Icelandic eruptions at that time. But did that have an impact, or did the society were affected by or responded to these eruptions or climate variations? This is a key question we are trying to address in this project. So what do we know, and how do we know? So, for example, one famous painting you probably all know, The Scream by Edvard Munch, here in the National Museum of Oslo, shows this colorful sunset, which is very likely related to the big, large eruption of Krakatau some years before, leading to this colorful reddish sunset due to sulfur building little droplets, shielding the incoming solar insolation, building kind of volcanic cloud, so less solar radiation reaches the surface, so it cools there. We also know some myths, especially Nordic myths about that, like the Fimbul winter or the Ragnarok. Here, showing the wolf swallowing the sun, the fear of a never-ending winter following, very likely, these big, large volcanic eruptions. We also have, in the past, we have deliveries, historical deliveries, and for example, here, reporting about the mystery dust wheel in 536 Common Era, the year of darkness, or the sun was dark and its darkness lasted for 18 months, John of Ephesus. So there were several deliveries we know about big, large volcanic eruptions happened and had an impact. Now coming to the geological time record, we also have ice cores. The ice cores in which you can see here, in Greenland and Antarctica, we can drill the ice, and they are an archive of the gases trapped in the ice at that time, or also of these sulfuric acid droplets from the volcanoes. So they are trapped, conserved in the ice, and then it's sinking down. So we can drill in the ice and get out an archive of, for example, the volcanic history of very large explosive eruptions. And by the way, the ice core records in Antarctica, they go back until 800,000 years. And right now, they have begun to drill in Antarctica for a new record going beyond 1 million, hopefully up to 1.5 million years. So the resolution, of course, is a key. How can we resolve these events? In the last 2,500 years, big advances have been taken out by the ice core records, showing yearly, sub-yearly resolution of these events. This is a study by Michael Siegel, which got published in 2015 in Nature. So now we have here a record with yearly and sub-yearly resolution. And we also have tree rings, which record, for example, if it was very cold during the growing season in summer, or even record frost rings, which you can see here. This is a damaged tree ring in 536. This is in Mongolia. And the tree have problems to grow when it's getting so cold in the summertime, so they get either a very thin tree ring or even a frost, as you can see here. If we combine these two now, you see this, the record for, in red, the volcanic eruption at that time for 536, 540, this double event. This is in red shown here. As larger the bar, as stronger the eruption was, shielding the incoming solar radiation. The first one, 536, was identified as an extratropical eruption in Northern Hemisphere, and the second one as a tropical one, but the community is still finding for the original source. There's a lot of research going on this. And then on the same side, you see now in blue, this tree ring temperature anomalies in summertime over Northern Hemisphere land, which really coincide. We get strong cooling in Northern Hemisphere summer land here, up to nearly 3 Kelvin cooling following the 536 event. This double event was also quite famous because it seemed to be connected with a big migration period and also the spread of the pest of the starting at that time in 540 and so on. And until now, the pest has been found at Skeleton until southern Germany, and they're still hunting to find the spread of the pest also in Scandinavia. So this is ongoing work. This event also have led to some other following eruption here by Ulf Bündgen, showing tree ring records for alpine and Siberia, showing temperature anomalies over the last 2,000 years. And I hope you can see here the coldest period of the past 2,000 years is here following this volcanic double event. And that led Ulf Dünken to call it the late antiquity little ice age, Lalaya, even to be colder than the little ice age here at around that time in the 17th, 18th century. However, there's ongoing debate about that, as Hilama published then following that paper, that not all tree rings show that pronounced cooling, and this is basically Alps and Altai. Other records show less pronounced cooling, as you can see here in the red, so not a century long-lasting cooling. So a question we wanted to address in the project is here, was there a volcanic-induced long-lasting cooling in the mid-6th to 7th century? And we also were hunting for more proxies, especially in Norway. What was the incidence showing here? So now coming to results from the project, and we have a challenge here. We have different disciplines. We are very diverse. So we have geologists, we have meteorologists, we have biologists, we have ice core record, archaeologists in. So we needed to understand each other. So at the beginning, we often had to transfer the language. What do you mean by that? That was a challenge. And we also have different scales. So this is a challenge, and so we're trying to link volcanic climate response to changes in society from a global scale down to Scandinavia and to the regional scale and even to the local scale to one side of archaeology evidence. And I will guide you through some of our results here. So first, we started with the modeling, and Evelyn did this work. We used a climate model to investigate if we enforce the climate model with this volcanic forcing data set over the 2,000 years, what is the response? Do the volcanoes really lead to that climate impact? And at the top, you see the global 2-meter air temperature for the past 2,000 years. You see it's varying, and the variation mainly comes from the big, large explosive eruptions. And you already can see here, over the 2,000 years, the period following this volcanic double event in the mid-5th century is the coolest here in that model setup. And then below, we zoom in now in the 6th to 7th century, from 520 to 680. And in greenish, you see the model mean, and we carried out 12 ensemble members, so we varied a little bit the starting point. So all the green curves is the model, and the black are the tree ring proxies, and the dash one are different compilations from different groups. So you can see how well that fits. This is here for Northern Hemisphere land, summertime. You also can see that in the model we have faster recovery than in the tree ring width, which is probably due to the too long memory in the tree over interpreting the coldness at that time. But you can also see we don't get a century long cooling. It's a multi-decadal cooling up to 15, 20 years, but not longer than that. So this work is public available, it's still in revision, and we hope we get through that in the next weeks. Then we wanted to further downscale, and now you see here Scandinavia, the map of Scandinavia. We are here in Oslo, and here you see now from the climate model the 2-meter air temperature anomalies. So all the blue basically shows that we get a cooling 15 years after the eruption, but also for the 536, 537, and 540, 541. So we get overall cooling. Then there's also an isoline shown here. This is a 5-degree Celsius threshold, which is shifting southward. So it's getting colder. And as you can see here in the model world, in 536 or 537, and 540, it gets even colder below 5 degrees, close to where we live here. The 5 degree Celsius is a threshold for the growing season. So if temperature falls below 5 degrees Celsius, then the plants, the vegetation has problem to grow. And I will come back to that. Here you also see now the precipitation anomalies, and basically it's brown everywhere for the ensemble mean, the mean of 12 runs. So it's getting drier over Scandinavia. However, when we look in the different ensemble members, 3 or 4 out of the 12, which I don't show here now, also have a wettening regionally. And we will come back to that. But with a colder air can hold less moisture, so this is what we expect. We get a drier air mass. But that can be varying if we consider the flow, different kind of circulation patterns. Okay, so it got colder and drier in Scandinavia. To further link and downscale, we carried out a case study for 3 areas. And this is basically Inga did, who was sitting here. He just finished his PhD on that work, Inga Gundersen. And so what did we do? First, we applied the growing degree day threshold of 5 degrees or below. So only if the temperature is 5 degrees or larger, the plants or the vegetation can grow. Then Inga used the meteorological observations from Norway from 1961, 1999, and projected that on a terrain model on Norway with the geographical information system GIS. On the left side, you see the summer precipitation. As we know, in the West Coast, it's raining a lot. We are lucky here in Oslo. And on the right, you see the length of the growing season applying this daily mean temperature of 5 degrees. So you can basically see, red, we have a long season, growing season above 200 days, and there's less inland and further north we go. Now, after setting up this on modern observations, we applied now a 3-degree cooling due to the volcanic eruption, as we have seen before, maximum 3-degree cooling. What's happening? And just to go back, we used 3 case studies, one in inland Norway, Gudbrandsdalen, one in the southwest, where we have a lot of rain at the coast, and then 3 close to Oslo and Rachnerhaugen, which I will show you now in more detail. So let's start with the first case, Gudbrandsdalen Valley in Hundorp. So this is here inland mountain valley area. So you see here a map, high resolution. The black here is cultivated lands. And we have some weather station here. Hard to see, but it's here in the middle. And we have pollen coring we carried out also in that area. And now you see already the result applying the 3-degree cooling. So it's blue everywhere. It's dropping below 1,100 growing degree days accumulated. And the local requirements in that area to grow for barley is above 1,170, or for oats, it's above 1,270 days, or for wheat, above 1,520 days. So barley, oats, and wheat cultivation are likely to fail in that area with a 3-degree cooling. Now let's have a look at the other 2. The second one is at the southwest coast of Norway in Forshant. So here we have now the local requirements have to be adapted for each area, taking temperature, precipitation, latitude, insolation, and the altitude into account. So here the local requirements and the threshold with 3-degree Kelvin cooling leads to that barley and oats may fail, and wheat likely to fail. So here is also still a failure possibility, but less clear than for the Gudbrandsdalen Valley Hundorp. And then we also analyzed Oslo area, Rachnerhaugen. This is next to the airport, Gardermoen, so I will tell you more about that. This is also a site we analyzed, and here, when we apply the local requirements, barley and oats are likely to mature and wheat likely to fail. So you see there's quite a difference in the different sites depending on topography and also meteorological impact. We also analyzed for those peat, box where we analyzed, Helge did this, our pollen in the peat box around that, which underline what we modeled here with the growing degree model. I'm not going in detail in that now, but you can ask questions further. But now I will dive into Oslo area, Rachnerhaugen. Okay, so Rachnerhaugen. Who has been at Rachnerhaugen and know Rachnerhaugen? These are the team members. Okay, so Rachnerhaugen is the largest mound in Scandinavia. It was built in 550. In front, and this is what you see here, you see the mound, which was built by felling thousands of trees in the surrounding and built up with pine and birch trees to build up this mountain. You also see in front of the mound there is, now it looks large, it's a small lake. It was, this is Lake Løkjotjern. It was built 10,000 years ago due to the remnants of the ice moving away and then building this little pond of this lake, which has no in or outflow. So we thought this is an ideal case study. We have archaeology, the build of the mound. We have trees, which were felled at that time to build the mound, so we can analyze that. And we have a lake to also analyze the lake sediment as an archive, what happened in the lake at that time, analyzing pollen and other material. And this Rachnerhaugen mound was 3 times excavated in the 19th century and in the 20th century, and already at the second time by Grieg. Here you see a chunk of that tree, and by the way, we have one example here for you. It's just a little piece of it. You will see the 536 tree ring, the very thin one, which is hardly to see, so it's hard to see, but it's a little circle, and we will give it a round. This is from the Rachnerhaugen mound and from the tree which were felled at that time. And hard to see, but this is actually here, the very thin, but you hardly can see, it's a 536, the year of the 536 eruption, which probably led to this very thin ring at that time. And there's ongoing analysis on the Rachnerhaugen trees. We have 3 samples, and this is John Bostek, Anhoop Jaren, who's sitting here in the CLIP lab. They're further analyzing that, and we will further work with that results. And here you can also see, or hardly see, this is a 536 event where there's hardly anything to see. Like before, it should be a darker ring, and this one is very thin and not that dark. We also analyzed, and this Kjetil did, who's also sitting here, Kjetil analyzed the C14 datings of archeological findings in the area. And the area we used here is for the Romerike. And at the right side, you see here, at the right side, you see here depths or calendar years from today back to 6,000 years. And here the C14 sum probability density is shown. It basically says when there were findings in the area, in this green area, then we get a higher probability density. So you can see in that area, C14 dates or cultivation started more than 1,500 years ago. And you can also see that there was a strong increase before around 500 and then a strong decrease in the area. Then we analyzed, and this is Manon, and where's Manon? Still also here. Then we analyzed the lake Le Chaudière. Manon, with the help from Eirik Ballo, Jostein Bakke from University Bergen and others, cored the lake Le Chaudière 2 times, and then analyzed the geochemistry, but also the pollen in the lake. And here you see the age model. So it's going down to 6 meters, covering here the Holocene, the past 10,000 years. Here you see actually how they were sitting, like were on a little floating deployment, and then they carried out, we were also joining them, carrying out this long pistol cores and also smaller ones. For this core, we have a sampling interval of 1 millimeter for the geochemistry, 3 to 40 centimeters for the pollen, and 70 centimeters for the DNA, for the very large, for the Holocene period. And now you will see a heavy figure, but I will guide you through that. So here are the results. So what we also did, and this is Annike and Sanne did this from biology. We analyzed pollen, Helge did that, but we also got biologists on board and analyzed the DNA in the same samples as the pollen. So now what you see is pollen fraction on the left, and to the next, the DNA replicates of the same species. And on the left, what do we see? We see anthropochores and apophytes. So this is cultivated direct science for agriculture, direct or indirect science of cultivation. And here's again, sorry, it's from 2000 down to 8,000 years before Christ. So you can see here, cultivation in that area in Rachnerhaugen started before Christ around 500 BCE. And what was, as we learned now, must be very special to analyze DNA and pollen from the same samples and that they show such a good comparison. That must be something very special. So we were extremely happy and lucky to see the results. And Annike de Schurre published this. Annike didn't have time to come. She also finished her thesis, PhD thesis on this last year. Then we also analyzed several cultivated species, hemp, cannabis, hop, rye, barley, and you always see the pollen and then the DNA, the pollen and the DNA. So it really matched very well. Then with the DNA, we were also able to analyze selected mammal taxa, which you can see here. Cattle, horse, pig, sheep, and goat. And some of you may remember when we were in Cambridge, there was a hypothesis from Frode, from our colleague, that if there's a big crisis, the horses, the cows will go down, but the pigs will go up. This we don't see here. The pigs, there is still an ongoing cattle and horse mammals in that area around the time of the crisis of the 550. So we don't see a clear reduction here. So this we cannot underline for Rachnerhaugen, which also fit then to our GDD model calculation. You also see charcoal and the C14 I showed you before. These are also signs for the archaeology, like the society, the cultivation of the Rachnerhaugen area. So now we can bring that all together in a synthesis. So here you see a map. Here we have our lake, Le Chaudière. Here we have our mount, the Rachnerhaugen Mount. And now you see the cultivation, the people living at that time. So the start of the agriculture in the region and the first farms were built in the Bronze Age. So this is what we see here, the Bronze Age farm in the vicinity of roughly 400, 500 meters away from the lake. Then in the we have the farming closer to the lake, which start around 200 BCE, and of course we have the build of the mound 550 CE. So this all has an impact then, of course, in the lake input, which we analyzed. Then, of course, the main target is not the Holocene in the project, but is the 200, the Viking Age. So we had a very high resolution around 200 to 1,300 CE. So here we really, and this is something novel, we went to go as high as possible. So geochemistry is still 1 millimeter, which corresponds to 1 year resolution. The pollen, we analyzed, or Helge analyzed, 1 to 2 centimeters, so that's roughly 18-year resolution. And the DNA to 9 centimeters, that was roughly 80 years resolution in the same sediment core. So, and here are some results from that. This is Manon published this. At the top, you see 2 published temperature reconstructions from Lundqvist and Christiansen and Lundqvist from 2010 and 12. And below you see our calcium-titanium ratio for the 2 cores we drilled in 2018 and 2019, which seem to reflect the temperature anomaly from Lundqvist. So we use the calcium-titanium ratio as a temperature proxy for that lake to get the local temperature anomalies during that time. And this is what you see here below, is then the temperature anomalies with lower temperatures in the Dark Ages cold period from 300 to roughly 600, and then a warmer climate following up from the 800 in the medieval warm period. So this is based on the Rachnerhaugen lake sediment. And here, take-home message from that part on the lake and is that the changes in the agriculture practices in that area show the following: that in colder periods, husbandry were dominating, whereas in the warmer periods, cultivation were dominating. So the pre-Viking society in southeastern Norway adapted to the climate variations. That was a conclusion we draw from that study, which is published beginning of this year by Manon Braja. To wrap now up the whole as we have it so far, different data and methods give evidence for volcanic climate changes impacting agriculture and the society, the pre-Viking society and the Viking society in Scandinavia and also in southern Norway during 200 to 1,300 CE. And here you see our best of synthesis, packing together our climate model results for temperature and precipitation, together with the proxies based on archaeology findings, different bog and lake sediments. How was at that time a likely scenario due to this 536, 540 event. You also see when we consider the larger area of the C14 dates in the area southeastern Norway, this pronounced sudden drop of findings, which relates to this crisis, the climate crisis in the migration period, which is really significant in the C14 archaeology data record. So we are not done yet. The work continues. There are further challenges, and I also will give some outlook. So the resolution to get this sub-annual to sub-decadal resolution is really a challenge, and we still try to bring the theses together to really link them. And for that, we need to work on the chronology and on the synchronization of the chronology. And we actually need age anchors, so that we really, for example, that we really can say the lake coincide with the ice core date and so on. And for that, we need to find cryptotephra. So this is a big target, to find volcanic ash, invisible ash, which we call cryptotephra, in the lake sediment. We're also working on Icelandic eruption impacts. This is still challenging us, so this is Hermann and Jeong are doing that. But also the data digitizing is an important point in the internationalization of the data. We also promised to help with an exhibition for the new Viking Age Museum, which is built in 2025, 2026. It got delayed, so let's see how we are proceeding on that. And just as an outlook, Eirik, who is not here today, he's in US right now, analyzing Lake Saktjernet, which is close to Elverum, a little bit north of Oslo. And Eirik's PhD thesis is on CT scanning. So we usually know the CT scanning from going to the doctor, but this we can also do with lake sediments. And here you see a CT scan of Lake Saktjernet, which is a dwarfed lake in Norway, which is the dwarfed lake we have found so far. And you see the lighter and the darker figures. These are the vars. And for example, here in the upper 2 meters, 5 to 8 vars per centimeter occur in the top 2 meters. So we get sub-annual resolution with that lake. And this is really a big goal. So this is a key for Eirik and for us to further work on that. And he's doing that right now. And then another challenge is the Icelandic volcanic eruptions. Herman and Chihong are working on right now, who are also here. Herman's is working on his PhD thesis, and Chihong is a postdoc. And we just have been in Iceland last year, going in the field, looking at the ash deposits from all the Icelandic eruptions. At the top 2.5 meters, we see Elgjá, 939, 940. Here's Thorvaldur Thordarson and Herman going through the record. And we are targeting Elgjá, but also another event, 752, 764, which is likely visible here. And both of them are modeling these Icelandic eruptions. And here you see some results for roughly 4 times the 536 eruption, so much stronger. So here, global surface temperature response would be up to 2 Kelvin. So in the northern hemisphere, that would result, I don't know, probably 4 to 5 Kelvin, much, much larger than in the global mean. So ongoing work. With that, I would like to thank my wonderful team, especially Frode, who's not here today, who guided us to many exhibitions. Thanks a lot. And to all of you, also for being here. And thanks for listening.
Yes, thank you, Kiki, for this wonderful presentation. It shows the cooperation between meteorologists, geologists, archaeologists. This is very, very beneficial in these times. So very happy for that. So now we are open for questions. You're far away.
Hi. Maybe I missed it, but you mentioned DNA samples of horses and cattle and pigs and so on. Where were these samples found? Can you say more about that? And how can you reliably make estimates on how many pigs and goats were kept by the farmers of the time?
Thanks for the question. So the DNA was analyzed from the lake sediments in the same, which from the coring from the core we draw. We took the pollen samples. We also took then the samples for the DNA. And for the DNA, you don't get absolute numbers. You just get, you can say there were pigs or horse, or there were none, but you can't say how many.
Pigs don't make pollen.
No. DNA, you find the DNA material. Is someone here from Sande is here? No. No, you, Manon, maybe you can help out? Is Manon here? No, you analyze, oh yeah, Manon, yeah. So the lake is a catchment, getting also the poo of the cows and the pigs, or also the DNA material which is in the sediment. So this is part of it.
Okay. I have a small question. In the start, you showed this 5 degree, which moves down after the eruption. That's the 5. This was the annual mean temperature?
That was April to September.
Oh, April. Okay. Thank you.
I think it was.
More questions? There is a question. I'm running.
Thanks, Kiki. This was fantastic. Amateur farmer here. I was thinking about when you showed the failure of the crops, or the potential failure of the crops. I don't remember. Yes, this study. You mentioned there, like, I don't know, 1,500 or 1,300 days. What is this unit? Because I don't understand. I mean, like wheat, for example, takes 9 months, 6 months to go from seed to harvest. So I don't understand those quantities.
So I think Inga can help out, but this is accumulated over the 30-year period. Is it?
I can answer. It's growing degree days. This means this is during you add up the temperature, the annual, the mean day temperature during the growing season. So it's the same like the thawing degree days, freezing degree. Also this the day, also degree days measure. So you add up the number of temperature for each day. So if a week with 5 degrees every day, then you have degree day for this week is 35. 7 times 5. Right?
Thanks, Ben.
More questions?
Anne has one. Anne?
Da.
Oh, you know, I think this is great, Kiki. Really intriguing how you put together the idea that colder times, more animal husbandry, and warmer times, more grain production. Did I get that right?
Yeah.
Do you have any ideas about the fact that those animals have a high grain requirement in order to take care of them, and that how do you square that with reduced grain production?
So I may also need Manon here, but I think this is what we show for the Rachnerhaugen area, that here in that area we likely see less failure. This is the one at the right. So it's presumably we don't have a big impact on the cultivation, and this is also what we seem to see in the pollen analysis. So then it would also not have an impact on what the mammals were eating, or But this is, of course, as far as we can come.
It would be interesting to pursue whether that means trading patterns were augmented during these periods, or I don't know.
Yeah. I think more to discuss, and this actually we want to write a synthesis paper on the Rachnerhaugen, bringing all in what we have understood so far and what we have newly done, including the tree.
Okay, there are 2 more questions. We start here, probably first.
Hi, thanks, super fascinating. I'm Dominic Collett from History. You have this wonderful acronym, VIKINGS, and I think maybe initially you also suggested that you would be able, or, interested in covering a longer historical time period. So because we're just starting a similar project in the later period, we'd like to learn from the challenges that you might have faced. So hands on heart, is that you focus on the 6th century event mainly because you had to prioritize resources, because your talk was a little shorter, or because you found it more difficult to find clear-cut impacts for the later periods? Is that something that you struggled with?
So, good point. So I also feel like, and Rode keeps on saying, well, we actually have to publish on the Vikings in itself. So here, in the study from Manon, you see we cover the period until 1300, but that is only for the lake Rachnerhaugen, for that area. So then you can see we hardly, and this is the cultivation, we don't have a lot of variations at that time. So we also had the medieval warm period which started up. So from that point of that perspective, we couldn't come up with so many new adding up the results. But we're still working on it. There will be a lot more coming on the Icelandic eruptions and especially in the 9th and 8th century. And we will try to put it together with the Viking. But then the question maybe we don't find so much. That's also a possibility, right? So it's ongoing. But I guess maybe that's the thing. The biggest change we see in the 6th century, in the archaeology record. It was the coldest period, it seemed to be the coldest period in Northern Hemisphere, summertime. So it's a good starting point, but it shows also the biggest changes. Until now, let's see.
Okay, then maybe the last question was here? No? Okay. Yes. Then I don't see any more questions. Then it's also 1 o'clock. Then I say once more, thank you very much for this intriguing talk from Kiki. Then I wish you back here in about 4 weeks or so, and I think Karen Meyer will give a presentation then. And until then, we will have a nice spring and Easter and everything.